In this video, I will describe some of the features of interactive plots in Nengo. The particular example I'm using can be accessed from the demos folder in Nengo and is called SPA_sequence routed. The function of this network is described in a different video, so I won't discuss it here. However, it is a useful network for my purposes, as it's defined in a 16-dimensional space and has about 5,000 neurons, and so it lets us see many of the features of interactive plots, allowing us to look at the data generated by this network in many different ways. The easiest way to access information about subnetworks or populations in a Nengo model is to right-click on the background of interactive plots. This pulls up a list of networks, their subnetworks, and any populations within inside those subnetworks. For instance, if I wanted to view the state buffer information, this is essentially like a working memory, I can click on that and it is then displayed with its connections in the interactive plots viewer. The plots available for any population or subnetwork can be determined by right-clicking on them. This is a population, and so we have several different kinds of graphs that allow us access to information about individual neurons and decoded values represented in that population. The basal ganglia itself is a network that has many subnetworks, and so it has different kinds of plots available to it. I would like to examine several of the plots available in the state buffer population, so allow me to quickly hide some of the other plots. The remaining plot is actually associated with the state buffer population, and so whenever I hover over it, over the population, the other one is outlined with a small gray line. Let me run the simulation again, and we can look at some of the plots that we haven't seen. The first is the value grid. This shows the same information as a regular value plot, except it plots it in a grid where each square is one dimension of the higher dimensional vector space. Because this is a 16-dimensional vector, we have a 4x4 grid. This same information can be seen in the regular value plot. In a value plot of a high-dimensional space, things can become very cluttered, and so when you right-click on this plot, you can select which values you would like to see. If we select all, it can be very difficult to discern patterns within this representation, and so the value grid is often more useful. We can also look at the XY plot that we've seen before. And in this case, we will be able to control which two dimensions are plotted against one another. Again, by right-clicking, we can set which dimensions we'd like to see on both the x-axis and the y-axis. We can also look at the firing rate plot. This is very similar to the voltage grid. However, it is a firing rate that has been averaged over time instead of showing the spikes and the sub-threshold voltage. I would now like to discuss the features of some of these plots. On any plot, when you right-click on it, you can add or remove the label. On value plots, there's often an auto-zoom feature. This allows the system to increase the maxima and minima plotted if the value represented in the population goes very large. On the rate plot, right-clicking shows an auto-improve and improve layout option. What this does, when you select it, you can see some of the neurons will begin to move around, because there is an algorithm running in the background that tries to put neurons with similar encoders near one another. This makes the representation often look more like a cortical sheet, since neurons with similar tuning curves are often found near one another. The plots I have been discussing so far are associated with the state buffer population. But in Nengo, different kinds of subnetworks and populations can have different kinds of graphs. For instance, a basal ganglia subnetwork has a graph called rule utility, which shows how similar the rules available to basal ganglia are to current cortical states. As well, thalamus has some special graphs, such as rule activation. The Thalamic Subnetwork is also displaying another feature of interactive plots. In the Thalamic Subnetwork, there are two output origins, one called channel vision state and another called rules. And you will notice that for each of these origins, a separate set of plots is available. I would like to conclude this tutorial by discussing some of the simulation features available in the configuration panel, which can be accessed by clicking the triangle at the bottom of the interactive plots. On the far left is a Save as PDF button. Clicking this button allows us to save the current view as a PDF, which is useful for publication and distribution. Clicking the Data button allows us to see and save the data as a CSV file, which can be useful for processing it in a different application. Choosing different modes allows us to run the simulation faster and slower and with different degrees of realism. The default mode is to run with all spiking neurons, rate mode runs with rate neurons, and direct mode does not run any neuron models at all, but instead simulates the dynamics of the vector spaces themselves directly. The time step parameter determines the length of time between simulation calculations. A step of 0.001 or 1 millisecond is our standard value. Decreasing this value will increase the accuracy of the simulation, however it tends to slow the simulation down significantly. The speed is the speed at which information is displayed in the interactive plots. If we set this to 1 time, we're attempting to run the simulation in real time. However, this is seldom possible, depending on the speed of your computer. It is usually limited instead by the time step. The recording time is the length of time that data is saved and available in the data viewer. As you can see in the above simulation, it has run for 6.64 simulation seconds. However, data is only available from 2.64 seconds because of the recording time value. Additional features are evident when I slide the window over. Here we can see the filter time. This is the time constant of an exponential filter, which is applied to most of the graphs showing values, for instance an XY plot or any other kind of value plot. 30 milliseconds, for instance, determines the length of time over which data is smoothed in these kinds of plots. The time shown value determines the length of time that information is visible on a plot. For instance, here because it's set to 500 milliseconds, the values on this semantic pointer plot go from 6.1 to 6.6 seconds. The disk icon will save the current layout, and the reset icon will restore the last saved layout. That concludes this walkthrough of the interactive plots available in Nengo. Additional information can be found in the documentation on our website at nengo.ca.